Thank you for the introduction, Paco. So my name is Irene Ballester. I'm a PhD student at the Computer Vision Lab in the Technical University of Vienna, and today I'm here to present a part of my PhD topic, which we can summarize in measuring dementia behaviors through depth sensors. So, I would like to start with an introduction and give you an overview why we are doing this and why this is important. And for that, I would like to talk about what's dementia. So dementia is a syndrome in which there is a deterioration in cognitive functioning beyond what might be expected from normal aging. And dementia is one of the major causes of dependency among older people. So we as a society have to find ways to ensure that the quality of life of people with dementia and their caregivers is maintained through this syndrome. In dementia, one of the characteristics is that the people not only suffer from cognitive impairment, but also from behavioral disturbances. And if those behavioral changes are strongly correlated with the degree of functional and cognitive impairment. So we can use this. If we would be able to measure these behaviors and these changes in behavior, we could use it as a proxy for cognitive impairment. However, these measurements happen when the patient goes to the doctor, and this is done in an episodic way, as you can imagine. And also, most of the cases, and often it's based on self-report. So if we could develop some technology that could help us to provide a complementary information to these assessments, this could help the practitioner either with diagnosis or with tailoring the treatment. To do so, we can use cameras, but as you can imagine, this has big problem with privacy. So in my PhD, in my topic, I focused on using depth sensors. As you can see here, they are not completely mitigating they are not completely solving the privacy issues, but they mitigate part of it. So of course, complementary measures are needed, but it's a way to protect the privacy of the user. So with this, this is the overview of my thesis. So the idea is to develop AI or more specifically computer vision methods for measuring the behaviors of people with dementia. In this case, we are focusing on care home residents using depth maps. And we want to do this for two reasons. One, in order to have an exhaustive remote patient monitoring, and also to provide assistance with the activity of the daily living. Today, in the past, I talked about providing assistance with the activity of the daily living with the toilet help. Today, I'm focusing more in what is an exhaustive remote patient monitoring and how do we do this with depth sensors. Just for you to have an idea, this will be the ultimate goal. So we will have in this graph here, we have the number of active minutes per day. In the y-axis and in the x-axis is number of weeks. So we would like to have these points in time and see how this changes over time. And if there is a change, then this information will be given to the practitioner, and he could decide if this important is relevant or how it's. He will be the one deciding, right? But what happens here is that right now we don't have a way to have these points, and this is what my PhD is focusing on, like how through cameras we can measure the different behaviors in order to track them over time. In here, this brings me to two of the research questions that I want to tackle here today. One is that we have different inputs in order to have this behavior measurement, and then that these methods should work in real-world scenarios, and so we have to ensure that they have a robust performance, and I will talk about this a bit later. For now, we'll focus on the different inputs for behavior measurement. And so we use depth maps. Those are the inputs that we can we get. So we could treat the depth map as RGB images and just treat them like raw. We could reproject back to the 3D space and have point clouds from depth, or we could extract skeletons from depth or point clouds and use that as input for activity, human activity recognition. In RGB, right now the current state of the art is that we do this intermediate step of going from RGB skeletons and then activity recognition. And this is why I focused one of my papers about doing skeleton extraction from point clouds. When I was looking into this, I realized that in the literature, most of the methods that work with point clouds, they treat each frame independently. They don't process it as a sequence. However, if we look into the existing work in RGB, the methods that perform the best, they do use this sequence information, and this is why we wanted to do the same with point clouds. See here, for just an example for you to notice why this is important. So imagine that this would be our input. We have 3 timestamps. If we will only take the last timestamp, we only see here one hand, and the prediction, our model really misses the other hand here. However, if instead we process the 3 timestamps, in the second one we do have information about where the hand is. So the prediction is way better than when we only use one. Even if it's not perfect, it's way closer to the ground truth. And this is why using sequence information is important. However, problem with formatting, sorry. However, the problem is that we have point clouds. Point clouds, it's a very expensive way of treating information because we have 3D information for each point. And just for you to have an idea, each person here has like around 6,000 points. And if we, on top of this, we have sequence information, this becomes increasingly computationally expensive. So we have to find a clever way to do this. One way, like most naive way, we would have to treat each point independently, feed it to a transformer, and then extract features from there. However, as I said, this is not possible. So what we do is that the same way more or less that is done for vision transformer, we take the image, we separate it into patches. Here we are talking about volumes because we are in 3D, and we extract the feature, which I'm afraid we cannot see, but he will be the feature. And then we also concatenate this feature from the local volume with the center of this volume. And this is what we feed to the transformer. We perform max pooling to extract the most salient feature. We use an MLP that will give us the 3D coordinates of here we had 15 joints. Here I wanted to show you the results. We wanted to compare our method with other methods. For this we used iTop front view. It's one of the datasets that there are not many datasets actually for point clouds or depth and human pose estimation. I divided here this into two modalities, into 2 columns, one single modality and here multimodal methods. And when I say multimodal methods, it's because they use both the depth image and the points. In our case, we only use the points, and this has different advantages. But if we compare our method, which is called Spike, with only single modality methods, we outperform the state of the art. And actually, we could combine our method because basically what multimodal methods do is that they extract the key points in 2D and then they reproject in 3D and they do some refinement. And we could use our method to do so also. Here are some of the results that we got, qualitative results and ablations. So before I was talking about sequence length, and we wanted to check how important is sequence length, and because we saw that in activity recognition and in RGB this is very important, but till which point. So we do see an increase in performance until more or less 3 frames, but we also see an increase in memory requirements, so we want to find the optimal point there. In the result that I was showing you before, we were taking only past frames, but we could also take future frames, right? So we could take some from the past and some from the future and take the intermediate one for prediction, like predict the intermediate one. And I wanted to check if this is actually better, and we see here that there is not a big difference between those. And another ablation study that we did is that here we cannot see, but what I wanted to show here is that we treat, in order to extract the features of the volumes, we treat them in independently within time, right? And what they do in activity recognitions, it's proven that the longer the sequence, the better. So we want to compress all the information as much as we can. However, this is human post-estimation, this is not activity recognition, and we still want to keep the structure. So we checked what happened if we will use spatial-temporal convolutions instead of only spatial convolutions, and there is an increase in performance. So this is why we show that using spatial convolution is a better option for human post-estimation. So just to conclude this part, as I said, sequence information is useful, but up to a certain sequence length. Also, and this is because my intuition behind this is that past timestamps that are very far doesn't have a strong influence in the current timestamp, so we don't need to consider those. I also said before that spatial convolution helps to preserve spatial structure, which is very useful for human post-estimation, and we achieved state-of-the-art in ITOP. However, like now we tried this in a benchmark, it works, and now the future work is to see how our method performs with real-world data, and this is what I'm currently working on. And actually this connects to the second part of my talk, which is the robust performance for real-world human activity recognition and actually also human post-estimation. And I would like to present you here the problem that we have. Yeah? We train and test our methods with benchmark data sets like the one here, and this is what we get when we collect the data in real-world scenarios. So yes, as you see, the camera in the benchmark is placed in the frontal view. We can see the person perfectly. However, for real-world data, it's not realistic that the person will be always facing the camera or the sensor in this case. We have to put it more in the ceiling. The person will turn around. The activities here, we see the person is just waving. In order for this to work, we wanted to actually be able to measure and to detect complex and natural activities. And then, of course, sparsity and noise, those are the problems that we are dealing with. In order to see what's the difference between the benchmark and the real-world data set, we do have to collect a real-world data set, and just I present here like a brief overview of what we collected. So connecting with the first part that I was not talking about, but the one for providing assistance with the activity of the daily living, we collected a data set for bathroom activities for people with dementia. So we had 50 full sequences of a person using the toilet. The participants were 19 subjects with dementia, and we collected 8 classes, so walking around, undressing, sitting down, sitting on the toilet, standing up, dressing, and washing hands. We did this in 2 different locations. So we have BAD 1 and BAD 2. BAD 1 we had 3 subjects, a total of 36,000 frames, and in BAD 2 we had 21,000 frames. And this is, of course, as you can imagine, an unbalanced data set because this was collected in a natural condition, so we cannot enforce that we have the same number of frames for each class, and this further complicates the training process, as you can imagine. So we have this data set with these depth maps, but what I will present now, we segmented the background and we reprojected back to the 3D. So these results are based on 3D point clouds, right? So what I want to present here in this table, it's the domain gaps that we found in this when we compare, when we work with real-world data. So if we take human activity recognition and we take one of the state-of-the-art works for human activity recognition, which is this P4 transformer, and we compare the performance of P4 transformer in their benchmark, so MSRI Axons 3D and NTU 60. The performance is around 90. There are other methods, performance is in the same like in the same trend, so up like over above 90. But when we do and we train in our data set, we can see here in the diagonal that the performance dropped from 90 to 53 or 63. So it works, but it doesn't work as well. This shows the performance gaps between benchmarks and real-world data set. What is even more concerning is that when BAT1 and BAT2, as I show you, is the same data set, just is this different location. So ideally it should work the same, right? However, when we train in BAT1 and we test in BAT1, we have 53. When we train in BAT1 and test in BAT2, then the performance drops to 7, which is just completely useless. The same happens with BAT2, right? So here we see that there is not only a gap between the benchmark and the real-world dataset, but also in scenes, and this is a problem that we have to tackle. This gap, we can also see it with human pose estimation. So I presented spike, and the result that I presented, it was for ITOP side. We get 89.19 when we train and test in the same one, but in this ITOP, it's very interesting. It's a very good data set because the same actions were captured with a camera on the top and a camera in a frontal view. So if we train in one and we test in the other one, the performance, as you see, drops significantly. And this is also another problem that we have to tackle. So we have also a performance gap between views, the same way that we had in the real-world data sets. So this is actually my current work. That's what I'm working now and still work in progress. But we are trying to find strategies to solve these domain gaps, and we cannot solve them at the same time. So I've decided to solve first this performance gap between views. And for this, my plan is to use test time training for domain adaptation in point cloud sequences. So what does test time training work? So in normal training, we will just have an encoder. For example, before I was talking about P4T, and then we will have a main task head that performs the classification or the regression for human pose estimation. And then we will train the encoder at the main task, and then we will freeze this, and this will be how we will perform inference. In test time training, what we do is that we're trying to find a self-supervised task. So what this means is that we don't need labels, so that this self-supervised task will bring our feature space closer to the one in the source domain. So if we look here into this diagram, we will have joint training instead of standard training. We will have an encoder, same than before, and a main task, same than before. But on top of that, we will also train a self-supervised auxiliary task head. And then we will training this in our joint way, and then this will be done in the source domain. Then we will move to the target domain here, and we will freeze both heads, both the main task and the self-supervised head. Why do we do this? Because we assume that in the joint training we already trained those heads enough. Now the problem is that what the encoder is getting is different from what it was getting before. So we want to fine-tune the encoder using the information coming from the self-supervised task, so that it will output something very close to what it was outputting before, with a very different representation as input. So that the encoder learns that this is it's kind of the same input, but it's different. So that's why we are fine-tuning only this. And then in inference, it will work same than before. We have both the encoder and the main task head frozen, and we perform inference there. However, here, as you can imagine, the problem is that, okay, I talked about self-supervised task, and yeah, but which task is it useful for us? So, for example, this was done already for point clouds, and one of the tasks was to do masking, yeah? So that we will mask part of the point clouds as input, and then we will try to reconstruct this masking, this part that are masked, and this was actually helping to bridge these domain gaps. And this is what currently my work is focusing, so we're trying to think, we're doing experiments to choose the right self-supervised task for this. So this brings me to the end of my presentation. I know I talked about many different things, but the takeaway message that I want you to receive is that we have seen very promising achievements in benchmark, but we cannot say that, okay, this is solved because it works well in benchmark. No, we have to check how do we behave with real-world data, and for this we need evaluation, real-world scenario, and potentially, as we have seen here, also strategies for domain adaptations in order to apply them to AAL applications. Future work in this area, we've seen a lot of foundation models for different tasks. We could also see how we can pre-train our models so that they are more robust for real-world applications. Here also one of the problems is the lack of label data. So we could also think how we can use self-supervised strategies in order to improve the performance. And something that I recently became interested in is continual learning, because we've seen, like, this method that I talked about, we assume that we will have all the information at the beginning in the training, but this is not true. We know that we will have to keep training our methods over time, and we have to have strategies that ensure that this training is efficient and it actually works after deployment. And with this, thank you very much. Ready for your questions.
Any question for here? Yeah.
So I have a question regarding the architecture.
Which
the first one with the transformer and the MLP.
Yes.
Okay, so because you also presented the results with like separate modalities, which are actually different parts of the body, like the landmarks and the multimodal one. So with this transformer, are you doing kind of, do you extract features for all different parts of the body or just for a single modality?
No, yeah, sorry, because it's a bit, the formatting is not good, but what we do here is that we take, we only make these local volumes so that it will fit in the transformer, right? But we are processing the full body.
Okay, which exactly transformer are you using? You're using encoder, right?
Yeah, the encoder of the transformer, right?
But, are you using some backbone, like a pre-trained transformer?
No, because we cannot really pre-train these things. Like, we could pre-train in other datasets that are similar, right? But here we are working with point clouds, so we cannot use standard.
Okay, so you're training all the parameters from scratch? In
this case, yes.
Okay, and how many parameters do you have?
Here, I think it was like 45 million, if I'm not. We had different. Oh, sorry. We had different sizes of the transformer, but I think the one that was working the best in total was like 45 million.
Okay, but I'm working with the text, but I know there are like these vision to Lagrange transformers, which are kind of backbones. I know, like CLIP and some else.
Yes.
Which like are 3-4 billion parameters, which can still run on a single computer. It's not. So, did you try to use these like as backbones?
Yeah, the problem is that those are point clouds with a different kind of input.
I understand. So you're using kind of time series. Different type of data, but still.
Exactly. So we will have to find a way so that we can leverage the data that they were pre-trained on, so that they will understand our data now, because it's a different kind of data at all, like completely.
Okay. And I also have a question for the final slide, the one we showed for the first. This one. So here, so you say during the test time you're training encoder, right? And then you are again, these are attention heads, right, that are frozen.
There are attention heads. No, there can be MLPs. Yeah.
Okay. And then so.
We can talk about that later. Of course. Yeah, of course.
Yeah, very interesting. Thank you very much, Irene.
Thank you.
Yeah, very interesting. Thank you very much. Just a quick, rather more generic question. At the outset, you pointed to the focus on behaviour change, and you had a list of different characteristic behaviour change that related to dementia. But is your focus then on identifying behaviour change in individuals? Because clearly you and I, our behaviours would be different, how we would show anxiety might be different and all the rest of it. Or are you actually looking for some generic measures that might have a broader applicability? Or is it too soon to tell?
Yeah, I'm afraid that it's too soon to tell. Right now I'm focusing on more like basic activity recognition, so I don't know, sleeping, eating. And then once we have this solved, I think we can move to more complex behaviors, as you said, like anxiety. And that's another problem because, as you very well mentioned, those will look very different among individuals. And also they are very rare. So, and we cannot simulate these behaviors. So that's why I was talking about continual learning, because these behaviors, I think we can incorporate them once we have deployed the system, and then we do have access to the real data, and then we can retrain the models. But yeah, that's a very good question. Thank you.
I have a question on the. Thank you for the presentation. So, on the one with the gaps between tests, and I don't have the number because some of your slide numbers disappeared.
Yeah, sorry.
Some are there, some are not, but it's on this one, yes. Maybe I did not understand exactly, but I think on this, the number on the bottom right, you say you have, if I understand well, on the left, on one side it's a real side, on the other side it's a test panel, and then it's the real world. So why is there 80?
Yes.
I think something is growing. This
Here?
one should be smaller. No?
No, so here, what the difference here, those are not real world and benchmark. The difference here, what it is the view in which it was trained. So the way to read this table is that it was trained in iTop, and when we test it in the same view, then we achieve a very good performance. Here, the problem is when we train in top and then the test inside, then is when we see the performance drop.
Okay, so because on the top I see real world scenes,
Yes.
but it's two different.
Thank you.
Any other question? So I have one.
So in the table with your reserves compared with the other ones, in the table that you have I realized that the only one that you lose is feet and knee. So in the legs, could be?
Sorry?
You lose only in and hips. From hips to the feet is the ones that you lose. All the others are fine.
Yeah. Why?
Why?
That's a good question. So the thing is that we are working with points here, and they are working with depth. So you have, what they do, most of them, is that they infer the points in the 2D and they go to the 3D. And in some cases that we have, the depth, the points are missing a lot for the lower body. But in the depth, the projection, you can still infer it better. That's my guess. I am not sure. We should have to check
because then if you have the real world data, usually the legs are going to be more occluded. So
yes,
you have already problems there, and then you will have more problems with the real world data. That's why I realized that.
Definitely, yeah. And if you see here, the thing that works the worst is the hands, yeah, for almost all of them, because that's the thing that moves them more, and they can have way different positions.
Okay, so it's time. So we are going to move to Victor. As most of you are from visual and then or from Good Brother, I forgot to tell people to present themselves. So Mladen Jovanovic, he's from Serbia, more in technological aspect. Malcolm Fisk from the UK, more on users. Yeah. And Dominique Archemore, more in assistive technologies. So that then you can talk with them later. From now on, please introduce yourselves. Okay, so thank you, Irene.
Thank you.
And then we move to Victor.